Hello everyone and welcome to the NPTEL course in Pharmacognosy and Phytochemistry. We are learning about few carbohydrate containing drugs, and in this session we will learn few more examples. These examples are the ones obtained from marine sources, which include sodium alginate and carrageenan, and a quargum which is obtained from the plant sources. To start with marine sources, let's discuss sodium alginate. Now, sodium alginate is a biopolymer which is obtained from seaweeds, especially if you see the brown algae which are there. So, this brown algae contains a slimy substance or a slimy carbohydrate, and that is what we are looking for when we discuss sodium alginate. So, it is a carbohydrate derivative which has been extracted using alkaline extraction, basically with a dilute solution of sodium hydroxide or potassium hydroxide from numerous species of brown algae, which include Microcystis pyrifera, Laminaria hyperborea, Laminaria digitata, Escophyllum nodosum and Durvilia leysionia. Now, this brown algae are located or harvested abundantly from oceans, especially the Atlantic and the Pacific Oceans. The good thing about this brown algae that they are growing naturally abundantly there, but in addition to that there are numerous attempts being made to harvest them, to cultivate them and to grow them so that they become more renewable. Now, how do you obtain sodium alginate? As discussed, sodium alginate is a slimy polymer which is located inside the cell of those brown algae. So, you need to extract them. So, first thing what is done is from this oceans or from the seas, the brown algae is collected. It's thoroughly washed off, because when it is obtained from sea sources, numerous tiny marine creatures get adhered to it. So, we remove those with washings. So, they are harvested, dried properly and then milled. The reason for milling is to expose or to break down the cells. Once the cells are broken down, the alginate which is located internally can be easily solubilized. Now, this consists mainly of acid like alginic acid, and you convert a sodium salt of alginic acid which is more water soluble. So, sodium alginate is extracted by exposing the alginic acid which is located inside the cell with an alkali such as sodium hydroxide or sodium carbonate to convert it into a water soluble sodium alginate mass. Now, this being soluble will be coming out and will dissolve in water. This solution is then further diluted. Why? Because if you take sodium alginate, it tends to form a little viscous solution, and because of increased viscosity, the particulates or the sand, dust or tiny impurities will not settle down. So, this is further diluted so that the impurities settle due to gravity, the viscosity decreases and then the supernatant is taken. Now, this supernatant, which is chiefly your sodium alginate, can be treated in two ways. Let us see both the cases. In the first case, what you can do is you can treat it with calcium chloride. Now, sodium alginate is a water soluble polymer, like I said, the sodium salt, but calcium alginate is water insoluble salt. So, it will tend to precipitate or form a little more rigid gel as compared to sodium alginate, and that is the reason this rigid gel forms a mass which can be separated by treating subsequently with hydrochloric acid. So, you can treat it first with calcium chloride or any calcium salt to create calcium alginate, and then subsequently generate or regenerate the alginic acid in presence of strong acid such as hydrochloric acid. Alternatively, you can directly use a strong acid such as sulfuric acid, in which you will get a precipitate of alginic acid, but this precipitate is still viscous, mucilaginous, and then needs to be purified further. So this is further purified or neutralized because it's acid and some acid residues will still remain. So this is washed and alkalized with sodium carbonate. Now again, when you do it with sodium carbonate, it's going to get converted into a sodium salt, but this time the water is restricted, and as a result it doesn't form a gel, but it forms a kind of coarse, greasy or coarse viscous solution which can be dehydrated to obtain your sodium alginate. Now if you see chemical composition of sodium alginate, it varies from different species of brown algae. The content also varies. So if you see different species of brown algae, the content varies somewhere between from 22% to 35% in most of the varieties. The sodium salt of alginic acid, that is your sodium alginate, is a very big polymer with a molecular weight of almost 35,000 to you can say about 15 lakh or so. So this has monomeric units of galluronic and mannuronic acid. Now this galluronic and mannuronic acid often associate them as blocks. So we can say 2 galluronic acid blocks, or 1 mannuronic, 1 galluronic acid block, or 2 mannuronic acid block. Now let's take an example of this. In this case, what you see here are 2 blocks of beta D galluronic acid, and here what you see are 2 blocks of alpha L mannuronic acid. So you can say this polymer to be GGMM linked. Okay. Now here if you see this, mostly what happens is the moment you treat it with an alkali, what you get is a sodium salt of this. This is what you call it as sodium alginate. Now this happens because sodium is monovalent, and here your carboxylic acid carries a negative charge. But imagine ions which have a valency of more than 1, say for example calcium. In that case, what happens is, because it's divalent, generally we get what is called, this is called as an eggshell model. So this polymers associate like this. So this is one block sugar, this is another block of sugar, another block of sugar, and here you will have your CO tending to form some association with this. Now this association is what creates or what makes your calcium alginate water insoluble. So this is like an egg in a box model, and you can see that's the reason your sodium alginate is more of a water soluble, whereas your calcium alginate tends to stiffen or precipitate depending upon the pH as well as the concentration of calcium ions. Now if you see the uses, alginate forms a nice clear solubilized jelly. So it is used in glazings, it is used to create soft creamy paste, it's used as a thickening agent, it is used as a stabilizing agent, a polymer for emulsions. It's good suspending and thickening agent, but when it comes to its emulsifying properties are not so good as compared to acacia and tragacan. More often being a carbohydrate, it acts as a very excellent binding and disintegrating agent, and that's the reason you will find them being used in tablets, lozenges. It is in food because of its transparency, it's used in jellies, ice creams, it is used for sizing again in textile industries. Now a little stiffer variants such as aluminum and calcium alginates along with potassium alginate have been also used in pharmaceutical industry. Now one application which I want to emphasize here is, suppose in case when you have your gastric ulcers. Now when you have ulcers in your stomach, when the food is being continuously digested, there is secretion of acids. These acids make their way into those ulcers and further irritate, causing lot of discomfort to the patients. So in this case, what is given is capsules containing sodium alginate is administered along with calcium carbonate. So calcium carbonate initially neutralizes the acid, but like I said, with food this will keep on evolving and more acid will be generated. So this acid will then react with sodium alginate and convert it into alginic acid. Now this alginic acid will form a nice viscous thick jelly like coating over your stomach ulcers or the inflamed area, and as a result this is protected from your stomach acids thereafter. So this is one interesting application where you can play with pH and still have pharmaceutical uses to this. Apart from this, sodium alginate has also been used in immobilization of enzymes and also as a media in biopolymers and bioengineering. The next polymer is carrageenan. Now carrageenan is also referred to as erismos, comes from a very beautiful fan shaped red algal species Chondrus crispus, also called as your carrageenan, and this belongs to the family Gigardinaceae. Now this is also one algal species found in Atlantic coast, your British Isles or in Europe and America. Now this fan like projections or tufted projections, this is something which grows very easily and rapidly, but this is stiff. You can say it's almost cartilaginous and may have a little underhues of green or dark purple. Now once you take it out from the sea, you can expose it to the sun. Once exposed to the sun, it will naturally bleach. A little amount of its pigment are taken care of, and as a result you will get a yellow translucent, the one that is appearing in, you get a dried algal sample in this form. So you get a translucent consistency. From that you can have different types of carrageenan being obtained. Now different types of carrageenan are actually obtained from different species of red algae. The different types of carrageenan are kappa carrageenan. Now kappa carrageenan is, if you see here carefully, we will discuss the structure. It has a sulfate derivative, a monosulfate derivative, and of all the carrageenans, kappa carrageenan is more rigid, stiff. So you can imagine a stiff jelly like your microbial media agar agar. So that kind of stiff jelly is given by kappa carrageenan. It's a thermoreversible jelly, so you can heat it and kind of melt it down, and it has a high gel strength, but it shows syneresis. So that means it will break and it will elute. We call it as whipping of gel. So that happens. Whereas iota carrageenan, if you compare it to kappa, this has two sulfate groups, and that's the reason it makes it little softer. So in terms of kappa, which gives you a little rigid brittle gel, this will give you a elastic little soft thermoreversible gel, but because it is soft, there is no whipping, there is no elution of liquid coming out. We refer to that as syneresis, and it's also thixotropic in nature. The last one contains about 3 sulfate groups. So you can see 1, 2, 3. So this 3 sulfate groups make it the most soft gel. Rather than it doesn't gel at all, it's just a viscositive agent. It has no ability or strength to form gel and to retain shape. So it's a cold soluble polymer, it's non-gelling and just imparts high viscosity. Now depending upon how much you purified it, you can also classify your carrageenan as semi-refined or refined one. The semi-refined is little opaque, contains more pigments and impurities. Some cellulose and fibers are also present, and the purity is kind of compromised. If you see the refined one, which is mostly used in pharmaceutical industry, it gives you very clear, transparent gel, and it has a good high purity and absolutely very lower concentrations of cellulose or other impurities. Now, if you want to see the sources of these 3 different type of carrageenans, the kappa carrageenan, the most stiff jelly one comes from Kappa ficus awarizi, formerly known as Eucremia cottony, and it is also obtained from Hypnea musciformis. Now if you see the middle one, the iota type, you get it from Euchema dendriculatum, or also known as Euchema spinosum. Now this is going to give you a middle consistency, little soft ones, and the non-gelling one but the viscositive ones are mostly obtained from your Gigartina species. Structurally, how do you prepare them? So this algae which grows on the rocks, you can just collect it. Again, they take a long rakes and kind of pull it out from the waters. The seaweeds are harvested. You need a good cleaning because you can see how much agglomerated that is. That needs to be cleaned of the debris or any impurities. So they are cleaned, bagged, sorted, kind of rubbed once so that whatever adhering impurities are there, they are all taken care of. Subsequently, they are washed, so anything such as soil adhere or sand adhering to it is also gone, and then they are subjected to hot alkaline extraction. During this, the carrageenan which is being extracted is dissolving in water, and then this dissolved solution is further clarified by filtration. In some cases, you can even remove or concentrate the solution by using membrane filtration. Now this being a carbohydrate, like your previous method, what you can do is to that aqueous solution, if you add a water miscible organic solvent like your methanol or alcohols, you can precipitate it. You can even precipitate by using salts such as potassium chloride. So once that is done, you get the crude precipitate. This crude precipitate is then dehydrated and converted into fine powder by vacuum drying, subsequently grinding, so that you get a good particle size. Now structurally, if you see carefully, it is a polymer which is made up of 3,6-N-hydro-D-galactose. So this is your galactose. So you can see here, you have your one galactose, you have your another galactose being here. So one is your alpha galactose, one. So you have your galactose being attached here. Now this is say one position, 1, 2, 3, 4, 5. So you have your monosulfate derivative which is attached here, and kappa has one sulfate attached to galactose, and there is absolutely nothing which is attached to a 3,6-N-hydrogalactose. But if you see iota carrageenan, there is one which is attached to your galactose, D-galactose, but if you see your N-hydro-D-galactose, that is especially your 3,6-N-hydrogalactose, you can see at your, this is 1, this is 2, carbon number 2, you will see one more sulfate derivative. Now coming to the last one, lambda. In this case, if you see here, this was your position 1, 2, 3, 4. Both of this galactose had sulfate at their fourth position. When you are talking about lambda, the sulfate changes from their 4 to second position. So you have your sulfate being there at second position on your galactose, and here this galactose is not N-hydro-D-galactose. Here you can see instead of that you will have your 1, 2, so there is a sulfate at second position, 3, 4, 5 and 6. So instead of forming a N-hydro linkage, you have sulfate at second as well as sixth position. So this is a little difference between the three derivatives, that is your kappa, iota and lambda, but they are not pure. Apart from that, they contain little other sugars as adducts. So when you hydrolyze them, apart from your galactose, you get your glucose, fructose and arabinose as well. Uses, so if you see this, it's used as excellent emulsifying agents. Carrageenans are good as stabilizing agents, solubilizing agent. I'll give you an example. If you've seen a gel based toothpaste, you see a good viscosity to it. So that's basically your carrageenan being used to make a stiff jelly. So it's also there as or used as hydrogels. Because of that consistency, it is used in tissue engineering. You get those films, transparent films, pellets or beads being prepared from it. You have your, like I said, toothpaste, creams, lotions and cosmetic products which are very clear. Your gels or sunscreen gels or some sprays or some viscous cosmetics, there they have been nicely applied. Apart from that, carrageenans have also been known for their antibacterial, anti-tumor and anti-hyperlipidemic effect. In food industry, it is also used in preparing milk products for imparting viscosity and gel-like consistency in ice creams, gels, just keeping a concentration of as low as 0.5 to 1%. Now we go to the third carbohydrate, and this is not a marine base, this is a plant base, and as you can see, this is our simple gawar or guar. This is Indian vegetable we often consume, and the seeds of it are used to prepare guar gum. It is also called as jaguar gum, and it is obtained from the seeds of guar, that is your Cymopsis tetragonolobis. Now this is a leguminous pod, so it's a Leguminosae family member, and this is abundantly cultivated in India, Pakistan, US, Australia and Africa. In fact, if you go to see, we are one of the global leaders when it comes to guar gum, and Rajasthan is one of a predominant state which gives you a major yield of guars gum, say up to almost 70% of the necessity required. So how do you prepare it? So here you have it. So if you take this guar seeds and grind it, you will see that the husk easily comes away. So initially you take your seeds of guar, nicely treat them or rub them with a cloth so that they are freed from any dust or particles. So they are kind of clean. Once they are clean, they are pressed into a mechanical splitter. You can see an image. So it kind of splits. So what you get is the outer hull is separated, which is almost 20% of its weight, and then you get an inner endosperm layer, and within that endosperm layer are the cotyledons. Now your gum is actually located in the endosperm. So I'll just show you. So if this is your guar seed, then you will have your endosperm layer. So this is much like your seed coat, or you can say your hull. This is much like your endosperm, and within this endosperm you will find two nice soft cotyledons. Okay. So if you do a or use a mechanical splitter, you can get this inner part. Now what we require here is the endosperm, because this contains the gum. So the splitter seeds are removed. You can get rid of the outer husk just by winnowing or blowing initially, and some separators such as cyclone kind of separators are used to get rid of it. Now in order to separate the endosperm, further processing is done, further little grinding is done. Now this cotyledons are comparatively softer as compared to the endosperm. So during the sifting stage, what happens is you can easily separate the cotyledons by winnowing once they are separated from the endosperm. So now you are left with heavy endosperms. This heavy endosperms, which are now, the hull is gone, the cotyledons is gone, this endosperm is pulverized. The endosperm you can see here is little grayish in color, but on pulverization it becomes whitish. So it is pulverized and micropulverized, converted into a fine powder, and that fine powder is what is sold in market as your guar gum. The inner cotyledons and other parts of it are still used in industry nowadays for preparing guar protein as well as in your animal fodder. Now what are the chemical constituents? So if you see the composition, this is again a carbohydrate. It consists of guaran, which is the main one, and guaran is a linear chain which is made up of mannopyranose. Guaran actually consists of a linear polymer of 1,4 beta D mannopyranose along with a alpha D galactopyranose. Now the galactopyranose are often attached by 1,6 linkages. So you can see a sixth being attached to first, whereas this linkages are 1 being attached to 4. So this is 1, 2, 3, 4, and this is 1, 2, 3, 4, this is 5, and this is the 6. So that is how you number it. So you will get this linkages. The ratio of galactose is to mannose. The mannose is always on the heavier side, with mannose being 2 times the galactose. This gum contains about 5 to 7% proteins, and that's the reason the resultant waste of the refining or producing industry goes as a animal fodder. Now in terms of uses, guar gum is used as a protective colloid because it's nice and mucilaginous. As compared to other plant gums, it is much superior in the performance as emulsifying. It is used as bulk laxative even for diabetic patients, and it gives you a feeling of satiety or fullness once you consume it. So it kind of, because of that fullness, it is also giving you what is called as appetite depressant properties, and it's also used in peptic ulcer therapy for the same reason, because it forms a mucilaginous coating over a peptic ulcer. It is an excellent binding and disintegrating agent. Now being a viscosity imparting agent, it's used in paper manufacturing, printing, polishing, foods, and also in cosmetic industries, where it acts as a stabilizer as well as viscositives. Now guar gum being abundantly available in India, one more interesting application is it is used to treat water. So guar gum is taken and you can take your effluent water. This is treated with guar gum. Guar gum eventually swells, entangles all the impurities in it, and eventually settles down. The supernatant, you will get it as a much clarified water. So that's there. Now being mucilaginous in nature, it has the same functions as other carbohydrates, such as it acts as a prebiotic. That's very good. The other part is for diabetic patients, it will cause a mucilaginous layer to be formed, and till it is itself digested into carbohydrates, that mucilaginous layer will hinder the absorption of carbohydrates and lipids. Now this has somewhere been also associated to the cholesterol levels. So consuming guar gum has shown to decrease your serum cholesterol levels, especially the LDL cholesterol, by almost 15% or 10 to 15%, or in some cases even 25%, without affecting much the levels of HDL cholesterol. Now like I said, because it inhibits, it is giving you hypoglycemic activity, because it will not allow the other sugars to permeate, and as a result, because it's not giving us sugars, it is also used as over the counter weight loss supplement. Apart from that, one more advantage is because it has decreased glycemic as well as decreased cholesterol, especially LDL cholesterol absorption, it is also reported to reduce blood pressure in patients. So these are few references if you wish to read further on these drugs, and thank you everyone for your patient listening.